So let's start simple and look into the relationship between one predictor x and one dependent variable y. So if we assume a linear model between those two variables, then essentially that means that we are assuming something like this, that the response is a certain coefficient beta 0 plus another coefficient beta 1 times the independent variable x, plus of course some degree of error epsilon. Now those two coefficients, beta 0 and beta 1, are what determine the model. Those are the two coefficients that one needs to specify in order to build a linear model between those two variables. So what do those two coefficients mean? Beta 0 is what we typically know as the intercept, although now some people in the computer science community especially, they call it the bias. But let's call it the intercept. So essentially what it says is that if we were to draw the line between y and x over here in this example, this line, this is the model, then beta 0 is where the model crosses the y-axis when x equals 0. So it's essentially the height, so to speak, of the line when x equals 0. And then beta 1 is, again, another constant, and it's what we call the slope. So it's essentially the slope of this line over here. It tells us for a unit increase in x, what is the increase in y. So if we increase the x this 1 unit, it's telling us this is how much the response is increasing. So again, the slope. The higher the coefficient, then the more steep the model. And if the coefficient is negative, then that means we have a negative relationship that could look something like this. And so beta 0 and beta 1 are the model parameters. They are what determine the model. Those are the two coefficients of the model. And so the whole point is we have a set of observations, a training set, and we need to build a model around those two variables. Essentially, that means that we need to find estimates of beta 0 and beta 1. That is, find a specific estimated model f hat. And if we have those two coefficients, then that means we could make estimates or predictions about the response given some value x. So we have a certain observation of x. Now we just plug that into the equation and we come up with a certain estimate for the response, y hat. And so the point is, of course, how do we find a good model? How do we find good estimates? Whatever good means. We're going to talk about it right now. And so let's say as an example, we have this plot over here, the y as a function of the x. These are the observations we have. And it's about thinking, what does the linear model look like? Now, of course, something like this would be completely wrong, right? We were, in this case, modeling a positive relationship when it's obvious that the relationship is negative. So, okay, we know that beta 1 has to be negative. All right, what else can we say? Well, perhaps a model like this would look appropriate, more or less. And so it would be something like, I don't know, beta 0, a good estimate might be about 5, more or less. And a good estimate for beta 1 could be something like, I don't know, minus 2.5, perhaps 2.5 negative. So for a unit increase in the x, again, we are going down the y-axis about 2.5 units. That could be a reasonable model according to this. But how do we do this automatically? And how do we define a good criterion to do this in an objective way, minimizing or maximizing that criterion? So in this case, we talk about the residuals. So let's say we already fitted the model. Say we have here again the example of the sales of the product by TV advertising. And let's say that we already fitted this blue model. That means we chose a specific estimate for beta 0 and a specific estimate for beta 1. Then we might ask the question, how good is that model? All right, let's think in terms of the difference between an estimate from the model and the true value that we should have fitted. So let's say that for any given observation I, we compute the estimate y as a y hat, and then what we could do is go through all the observations in the training set, in the training data, and look at how different is the prediction from the model with respect to the true value that we have in our data. And so we can define the residual for every observation I. We can compute the residual, let's call it E. which is the difference between the true value in the data minus the estimated value that we get from the model. And so think about it. If we have a residual that is positive, that means that the true value for that observation is larger than the estimated value. And so this means that the model is underestimating the value that it should produce. It's underestimating the outcome for that specific point in the x-axis, in this case the TV. If the residual is negative, then that means that the true value is less than the predicted value. So this means the model is overestimating the sales in this case. And then we can think about all those distances between the true value that we have in the data and the value estimated by the model. So if, for example, we focus on this observation, what we have is that the true value is larger than the estimated value because this is y and the estimate is all the way down here in the model. And so we can think about this distance. In this case, y is larger than y hat. So we are in this case, the model is underestimating the sales for this amount of TV advertising because it's saying it's around here, like 13, and it should actually be closer to 20. So this is the notion of residual. It's the difference between what the model estimates and what the model should have estimated in case it was a perfect model. And so thinking about the residuals, and in particular thinking about all the residuals in the training set, we could come up with this term, the residual sum of squares, the RSS. So it's essentially summing over all the instances in our data set, what is the magnitude of the residual? Let's say the residual square. And so whether we have a positive or negative residual, still we are accounting for how much the model is mistaken when making a prediction. So what's the distance between the true value and the estimated value? And so the square allows us to ignore the residual sign, whether it's positive or negative. We are only interested in the amount of error. It's going to also point in the direction of high residuals, because if we have a very high residual, when we square it, it's going to be even higher compared to the others. And so it's going to hint us in the direction that there might be certain observations that are estimated very poorly by the model. And it also happens to have some interesting properties that we're not going to get into in terms of differentiation and everything. But the point is that if we think about it, we could, in principle, choose the model that minimizes the residual sums of squares. So we want to choose the beta 0 and beta 1 such that the residual sum of squares they produce is the minimal that we can possibly have with the data we have. And again, assuming a linear relationship. So it's about choosing the two coefficients that minimize this quantity. And it turns out that one can do the math, and we have a nice close solution to this problem. And it turns out that the coefficients would be beta 1 computed in this way. You see, it has to do with the difference between every observation and the mean in the X, the difference between each observation, the response, and the mean in the response. And then here we have something that looks like the variance of X. So it actually has to do with the covariance between the two of them, how well they're correlated. This is just the equation for it. And then once we have beta 1, we can have an estimate for beta 0 in this way. And it turns out that these two equations give us the linear model that is optimal in the sense that it's minimizing the residual sums of squares. And this is known as ordinary least squares, or OLS regression. So that's good. So what we're saying is that whenever we have one dependent variable and one independent variable, we assume a linear relationship. Therefore, we have to fit a beta 0 and beta 1 coefficients. One way of doing that would be minimizing the residual sums of squares. We know the intuition behind it, what it's actually doing. We plug the numbers into these two equations and we get our two estimates. So we're building a linear model based on data and following a very specific criterion for how to fit that model. So what's the effect of the training data on the data we use to build the model? Well, let's assume here on the left, we have this true relationship between y and x. Again, this is something we never know, but just for illustration, let's pretend that y is 2 plus 3 times x. So the true model should look something like here in the left. Okay, we carry out a study, we sample some data, and what we have are these red dots. Those are the observations, our actual data. Let's say we have here, I don't know, 30, 40, 50 points in the scatter plot. So if we do OLS to fit the model, we have the one in red. And of course, we know it's not going to be exactly like the true model because we have some variation in the data, and it's very, very unlikely, or to say impossible, to get exactly the right model, but we get something pretty close to it. Right? Okay, let's say we change the data. Maybe we replicate our study and we gather some new observations, some new numbers, we fit a new model, and that new model looks like this line in red here. Again, it looks like the true model a little bit. It's a little bit different, but the point is that it's different from the one we fitted earlier. The thing is, of course, depending on the actual data we have, we are going to come up with one model or another. Each of those red lines represents one possible model fitted with one possible sample of data from this true model. And so the coefficients we fit, the beta 0 hat and the beta 1 hat, depend on the actual values we have in the training data. So, okay, we can fit the model. How can we say if the model is good? All right, then we talk about diagnosing the linear model. What should we look into when building a linear model? Well, the first of all is that the residuals should be small, right? After all, that's what we're optimizing. We're optimizing the amount of residuals we have in the model given the data, and they should be fairly symmetrically distributed. So if we were to look at the distribution of the residuals, we would expect everything to be around 0, meaning there doesn't appear to be any bias in the model. We're going to see an example. And also there should be no relationship between the residuals and the fitted value. After all, if there is a certain relationship, that might hint into a possible relationship again that we are missing between the independent variable and the residual, and therefore the model should try and incorporate that relationship into itself to get a better description of the data. So let's look at the example again. We have here TV advertising and sales. We assume the following class of models. Sales is beta 0 plus beta 1 times TV advertising. We do OLS. We fit the model. It's this one in blue. So our estimates are 7 for beta 0 and 0.05 for the beta 1. Okay, that's what the model looks like. Fair enough. What should we look into? Well, first of all, the distribution of the residuals. So we can look at a histogram of the residuals, and it should be kind of symmetric around 0. In this case, it's not really symmetric, so we have some more observations here than we should. But yeah, you could say it's fairly symmetric. Okay, let's just assume that this is a good model. Looks kind of fine. The second thing we should look into is the relationship between the residuals and the fitted values. So we could actually produce a scatter plot of the residual by fitted value. And this should look like a completely random cloud of points, meaning there's no relationship between a specific estimate and the residual of that estimate. And so in here we see something more striking, right? We see that, first of all, there appears to be a certain bias for low values, because it looks like the residual is always negative whenever the fitted value is small. And that actually has to do with how the model is not really capable of accommodating these data points over here. And it looks like the larger the value, then the larger the residual, right? It looks something like that. It looks like there's something funny going on in the data. And that's actually an indication that the residuals over here are much larger than the residuals over there. And this shouldn't be the case. It should be kind of constant. In the coming videos, we will see exactly what this means. This is something called heteroscedasticity, but don't worry for it now. And so the point here is that we have a linear model. The blue line looks like a reasonably good model, but we are already seeing that it could be better if, for example, we had this relationship looking something like this. We will see in the coming videos again how to properly model this. But for now, we see the kind of things we should look into when building a linear model. So how are the residuals distributed? And what's the possible relationship between residual and fitted value? There should be no relationship. So those are kind of qualitative diagnostics of the model. Let's look into more hard numbers to look into. So when we talk about the accuracy of the model, we could think about, for example, the residual standard error. So it's the standard error in the residual. So it's essentially this formula here. We take the square root of 1 over n minus 2. Remember, n is the number of observations. And what we take is the sum of the residual square divided by n minus 2 and then the square root. And so the higher this number, the worse the model, the higher the standard error. And the lower the number, the better. Now, many times it's a little bit difficult to think about that. What a lot of people prefer, again, especially in computer science and especially when we build a model for the purposes of prediction, is the root mean square error, or RMSE. So what we do here is take the square error for every observation. So again, this part over here, then do the mean, that's why I divide by 1 over n, and then the root square of that, which is this one here. So essentially something quantifying the amount of error in our prediction. So it's about taking all the residuals, square, and then essentially the mean of that. So again, the higher this number, then the worse the predictions are, or the farther they are from reality. Ideally, we would be looking for an RMSE of 0. This is, again, very useful for prediction, essentially what we look at when we care about prediction. But if we really care about how well the model reflects reality, how well it's able to explain the variability in the response, then we would look into the coefficient of determination, or R-square. So what we could do is take a look at the total sum of squares in the data. And it looks something like this. For every observation in the set, what we do is take the distance between the observation and the mean response. So, this is something that looks proportional to the variance in the response. So this is the total amount of variation we have in our data. And then it's about how much of that variation is the model really accounting for, or it could be explained by the model. Whatever is left is what we have in the residual. So we could compare the amount of variation total and the amount of variation we have in residuals. And it would be something like this equation here. So the total minus the residual over the total. So what amount of the total is being explained by the model? So this is typically what we prefer to when we think about properly understanding the data or the process behind the data. We want to build a model that accounts for as much variability as possible, regardless of whether it makes a very good prediction or not. Normally, if you have a good R-square, you're going to have a good prediction. It's not always the case, but this is a much better indicator of how good the model reflects reality. And it's going to range between 0 and 1. If we have an R-square of 0, that means we are able to explain absolutely nothing about the data. It would be a model with no predictor whatsoever. And then if we have an R-square of 1, that means we have a perfect model for the data set. That means we have a model that goes exactly through all the observations. There's no residual. The model is perfectly fitting the data. And it turns out that in this case in which we only have one independent variable, the R-square is actually the square of the Pearson correlation coefficient. So if we were to compute the correlation between X and Y, and then take the square of that, that's precisely what the R-square is measuring. And it kind of makes sense, right? If we have a line that looks like that, and all the observations go through that line, we would have a correlation of 1, and we would also have a R-square of 1, meaning there's no unexplained variability. Now, a question for you is, if we observe an R-square of 1, does that mean we have the true model? So does that mean that our estimates are equal to the true values, the true model generated in the data? Think about it. Well, no, it means it goes through all the observations in our data, it doesn't mean that we have the model generating the data. So let's imagine we have the relationship between y and x, and we only have 2 observations. Then sure, given 2 observations, we only have one line essentially going through there. That's a model that perfectly fits those 2 observations. Is that the model generating the data? Well, no, the model generating the data could be something like this. That's it. So just keep in mind that whenever you have an R-square that is very high, it does not mean that you have a model that resembles reality. It means you have a model that is good at explaining your data set, but might be still a very poor model of reality. So just as an example, if we go back to the case of sales by TV, this would be the OLS linear model. And in this case, we have an RMSE of 3.2, and we have an R-square of 61. So that means if we take a look at all the variability across the y-axis, then 61% of that variability is explained by the model. There is about 39% of variability in the response that is still residual, that we don't know where it comes from. Still, okay, is there anything odd about this model? Yeah, there's the part of growing residuals with high values, that's what we said, and also it's not really capturing the non-linearity of the relationship. We are forcing a straight line when we see that a better model would actually be something like that. Still, it's a useful model telling us that there is this positive relationship between TV advertising and sales. And at this point, it's very important that we talk about 2 caveats when fitting a linear model. Let's use an example. Let's say here we again have a relationship between y and x. Those are our observations, like 200 of them. Think about it. What would be a reasonable model of this data? I'm sure that most of us would say, well, it's something like this black line, right? It's the model that says y is 5/2 times x. So it crosses at y equals 0, and the slope is 2.5. Looking at the data, that seems like a very good model, right? Well, it turns out that if we do OLS and we minimize the residual sums of squares, the model we get is actually this one in blue. So let's say we fit the model f of y given x. So we fit the model that looks into the relationship of y as a function of x. And it turns out that is equal to 2x. So the OLS model is y equal to x. So again, it crosses at 0, but the slope is not 2.5, it's only 2. And one might wonder, why is the OLS fitting that line instead of the black line that looks a lot better? And the key point here is that we have to keep in mind that the residuals are measured vertically. They are not measured orthogonal to the regression line, they are measured vertically. Remember that what we look at is the residual equal true value minus estimated value. So that's the vertical distance between the true value and the estimated value. And so essentially what we are minimizing is this vertical line here in blue between one point and the model. While intuitively what we were trying to minimize when fitting the model in black, or when trying to figure out what the optimal model looks like, we were optimizing something that is orthogonal to the regression line. But that's not what we're doing with OLS. That's something else. There's actually something called orthogonal regression or orthogonal least squares, but that's not what we're going to cover in the course. So just keep in mind that what might look like the perfect model in your eyes is not really what OLS is necessarily fitting. And the second caveat actually has to do with what happens if we swap the 2 variables. What happens if instead of building a model of y given x, we build a model of x given y? One might think, well, it's just about doing the math and turning the coefficients the other way around. So if we have y equal, in this case, beta 1 times x, then one could think, all right, then a good model for x is 1 over beta times y. It's actually, again, not what's going to happen. So if we get this data set over here and we try to fit the model of x as a function of y, if we do OLS, then we come up with this red modeling here. So again, we see the model f of x given y equals 1/4 y. And we see that it's really not the inverse of what we have here in blue. In here we had 2x. In here we would have expected 1/2 y, but no, we have 1/4. Why? Because again, the distance that is being minimized is the one vertically from any observation to the regression line. So in this case, it's this red distance over here. If you think about it, what we are minimizing in the left is vertical, and this red model over here is like if we were minimizing this one horizontally. So it's not only that the apparently optimal model is not what's being fitted by OLS, is that it depends on whether we do y as a function of x or x as a function of y. And actually, if we look at everything, here's where we can compare. So over here with the dashed line, we have the actual inverse of the model here. So we have the inverse of the model that tries to predict x as a function of y, and it would be 4x. Where in this case, we have the inverse of the model that tries to predict y as a function of x, and it's actually 1/2 y. So modeling y given x produces a different fit from modeling x as a function of y. So this is something that we have to keep in mind when building our models. It really makes a difference whether we do one thing or the other. We can't just swap the two variables because they're going to mean something different. At least if we do OLS. Again, if we do orthogonal regression, like in the black line, it would be something different because in both cases, we would have exactly the same model.